So my name is Kevin. I'm on the right there. I'm the Director of Marketing. I'm simply doing the hosting today. I am very pleased to have two of our staff members on the presentation today. So one is Dr. Gabriel Gosselin, who is a SAR scientist at PCI Geomatics. And Gabriel has been working with polarimetric data for a long time and was the subject of his PhD research. And Jean-Sébastien is responsible for technical solutions. He's a specialist with all of our technology, and he's going to be giving you a little bit of a walkthrough on how it is that the processing looks like in our software. He'll give you a bit of an overview of the different functionality within Geomatica to produce some of the results that are going to be shown. So just a few quick words about PCI. If you're if you haven't been to our website in a while, or you'd like to kind of refresh yourself in terms of how PCI positions itself in the marketplace, we essentially provide flexible and scalable solutions. And what we mean by that is what you see on this slide. We have solutions that allow you to process imagery at different scales and allow you to deploy our technology to multiple users or to scale up for different levels of production. So we have Geomatica, which is our desktop application software, and we also have GXL, which is our high volume production system. And in between we have Python, which is an open source programming language, as you know, and that allows us to extend and scale and integrate our technology with other technology, and it forms the foundation or the platform of our technology offering. So our customers can achieve operational efficiencies through the deployment of this technology at different scales, and they can also scale it up or down depending on the production needs that they have or what it is exactly that they're doing. So that's a quick overview on PCI. At this point, I'm going to pass it over to Gabriel and Jean. They'll be continuing the webinar for the rest of the hour here. So over to you, Gabriel.
Okay, so thank you, Kevin. So now what we'll do for the next 15 or 20 minutes, we'll have a look about a little bit of the theory behind the compact polarimetry. We'll see what is compact polarimetry, how does it compare to full polarimetric acquisitions, and I will just describe briefly the different tools we have developed for the Geomatica version 2016, the tools that you will be able to use to process your compact pole imagery. And later, Jean-Sébastien will review those aspects by giving more examples and by actually showing how to use those tools. So let's start with a big question. What is compact polarimetry? And I will be brief here. The compact polarimetry is an acquisition that is, we'll say, similar or comparable to fully polarimetric acquisitions. For all the targets that are azimutally symmetric, so that means that they have a symmetry plane, you can retrieve the same information that you have with a fully polarimetric data. Now, of course, since we're transmitting only one channel, the information is comparable, but it's not totally the same. So we'll try to see what kind of information we can get and how we can compare the full quad and the compact pole acquisitions. So here I have a table that just do an overview about the different compact pole acquisition mode. So like I've said, the main difference between the full quad and the compact pole acquisition is that instead of transmitting two signals to the ground, we will send only one signal. And like for the full quad acquisition, we will receive the backscattering signal with two polarization. Now there is many compact pole mode available, and here there are three main compact pole mode that are listed. There is the pi over 4, which consists of transmitting a linear 45 degrees polarization, and then you receive your signal in the horizontal and vertical polarization. You also have the DCP mode, which consists of sending a right-handed circular polarization, and you receive the backscattered signal in right and left. And you have the CTLR configuration, which is the configuration that have been chosen for the RadarSat RCM. So it's possible to a certain extent to reconstruct quantum examples. But why the engineers or the different spatial agency have introduced the compact polarimetry mode? It's mainly because for an operational point of view, one of the main limitation of a fully polarimetric acquisition is the SWAT. Typically, a compact pole acquisition will be double SWAT of a fully polarimetric acquisition. Why? Because since we have to send two signal, so there is less time for the signal to reach the far range of your image and to come back. So since we have to double the pulse repetition frequency, we have less time to collect measurements. So this is why the SWAT is small for a full quad acquisition. So we have a larger spatial coverage with the compact pole mode. And one of the main reason is this is systems that are simpler to build, and this at reduced cost. There is less engineering involved. Now, what are the current and the future satellite that will have an operational compact polarimetry acquisition mode? Actually, there is two sensors that are already in space that have such capabilities. There is the Indian RISAT satellite, and there is also the Pulsar 2, the Japanese satellite, which is ALS Pulsar 2. And both of them have the CTLR configuration. And in the near future, there will be also the Argentinian SAOCOM satellite and the Canada RCM mission, the Constellation. And right now, we're already supporting the RISAT satellite. We will be supporting the Pulsar 2 mission in Geomatica 2016, and we will add, once we will have the data, or at least demo data, we will start the support of the SAOCOM and the RCM mission. Like I've mentioned at the beginning of the presentation, we have implemented many tools to process compact pole imagery, and we'll look at those tools. But let's just start with a slide that depicts now the two main workflow that we can use to do a compact polarimetry analysis. Right now, since there is not many compact pole or compact polarimetry sensor available, what we can do is we can take a fully quad polarimetric imagery, we can synthesize a compact pole dataset, and after that, if we really want to check what kind of information we have lost in the process, or how can we compare a fully polarimetric image to a compact pole dataset, depending on a specific configuration, we can then reconstruct a pseudo-fully covariance matrix and then proceed to a full polarimetry analysis. This is mainly for here science. So we really want to know what kind of information we're keeping and what kind of information we're losing when we compare a compact pole. There is the other workflow, which is more operational, is we work with, let's say, a native compact polarimetric image. We can, after that, use tools that are specifically dedicated to the process of compact pole imagery, and then proceed to a compact polarimetry analysis. But if we want, we can also use those native compact pole imagery and then reconstruct a pseudo-quad covariance matrix and proceed to a full polarimetric analysis. So this is three options. And we have tools to cover all those situations. So in Geomatica 2016, we will have a full set of tools to handle all those situations. And here listed in red, you have the main tools that you can use to do your compact pole analysis. We have a program called PS Compact, which is used to generate or to synthesize a compact polarimetry dataset from a fully polarimetric imagery, and you have the three main compact pole mode that we have described in the first slide. You have also another tools that is already available in Geomatica 2015 called PSS2C. So you can generate any compact pole mode. You can generate two coherent channels with any configuration of transmitting and receiving configuration. And this tool can be used if you want to check some calibration issue with your data. And those three are also new tools. We have PSComDis. That is a decomposition that is specifically dedicated to the process of compact pole imagery. We have PSComDec. This is another tool that has been developed specifically for compact polarimetry images. And you have another tool called PS Recons, which is used to reconstruct a pseudo fully covariance matrix from a compact pole dataset. And all those tools are available using in a graphical user phase environment in Focus Modeler, and we'll see some examples later on. And you can also have access to those tools using Easy or Python. Now let me we'll take now 5 minutes to describe in more details those tools. Like I've mentioned, PS Compact is used to generate one of the three main compact polarimetric modes. The CTLR mode corresponds to the Riverside constellation mission, which consists of, in sending a right circular transmission and receiving H and V. And with this information, you will do your analysis. And you also have the DCP and the pi/4 mode. PSComDis. This is a tool to generate discriminators. And the PSComDis tools is based on the Stokes vectors. So what you have here is you have your two compact pole channels, and what you're looking is the total power. You're also looking about their difference, and you have also the phase between these two channels. And based on those Stokes vectors, you can compute many discriminators, like the degree of polarization, which says if a specific target, or let's say an area of interest, is well polarized or not. You also have the degree of circular polarization. You can compute the degree of linear polarization, the polarization ratio, based again on the Stokes vectors. And the list continue. And some of those discriminators are comparable to the discriminators you have for a full quad analysis. Now you have here the alpha angle and the entropy that can be used to compare directly to their equivalent in the case of a fully quad or fully parametric analysis. You can also compute the coherency, the relative phase, which is not in that case the phase difference between HH and VV. This will be in the basis of your two compact polarimetric channel. PSComDec is another algorithm that is used to estimate the level of double bounce, single bounce, and volume scattering. And for one of you who are familiar with the full quad analysis, this is the equivalent, not similar, but the equivalent of the Freeman-Durden decomposition, which allows you to compute the same three parameters: the volume, the surface backscattering, and the double bounce backscattering. And when array of the scientific papers, there is mainly three different ways in which we can use to estimate those: the volume, the double bounce, and the surface component. We can use a degree of polarization to estimate uh, those scattering type. We can use the relative phase, or we can use the alpha angle. So here this is just some details on how we can compute those different backscattering type. So I won't just explain all the mathematics. You can after that come back to those slides if you want. But just to remember that depending on, and you will see it later on, just depending on which kind of compact polarimetry mode you are using, and depending on which of this version of PSCOM that you are using, you can get slight difference into the, let's say, fraction of double bounce, surface, and volume among your different tests. So in the compact pole analysis, there is still some room to understand what are to constructed pseudo-quad data is to have a better idea on how those parameters compare to the original version extracted from a fully quad data. And finally, the last tool I want to present you is PS Recons. So like its name says, this is a tool that is used to reconstruct a pseudo-fully covariance matrix from a compact pole dataset. So you have two channels, two coherent channels, and you want to estimate a covariance matrix. So there is a lot of unknowns. So based on a transmit and a receive configuration, you will combine those elements, and what you want to do is to create your covariance matrix, and you have to do some iteration because this is not possible to directly reconstruct a pseudo covariance matrix from your compact pole data. You have to iterate through your transmit and receive configuration and do some averaging to estimate this covariance matrix. And when you get a convergence, mainly to estimate the HV, because the HV is a really important measure, but unfortunately with the compact pole analysis or with a compact pole data set, we never have a pure measure of HV. So we have to reconstruct this HV. And based on this reconstruction, we will estimate as well the HH and VV component from your compact pole channels. And then you end up with your final pseudo-quad covariance matrix. And we can reconstruct this matrix, but as you can see, there is some information that is missing. And just before I hand over the presentation to my colleague, the big question is, and this is still an open question, imagine you have your compact pole dataset. Is it better to, from this compact pole dataset, to reconstruct a pseudo covariance matrix and then proceed to a conventional full quad analysis, or is it better to use the tool specifically dedicated to the processing of compact pole data? This is two avenues you can follow, but still now there is no clear answer about which is best, which one is best.
So the goal of doing this right here is to associate the theory that Gabriel just presented with the new compact polarimetry tools available in Geomatica 2016. So to do this, I'm going to show you two workflows that I would have went through, and afterwards, or immediately afterwards, I'm going to present the results, and I'm going to compare the results from compact polarimetry to full polarimetric images. Okay, so here we have our first workflow. And the purpose of this workflow is to generate decomposition parameters using a pseudo-full polarimetric scene that was reconstructed from a compact polarimetry scene. Then compare those results to the original full polarimetric scene. So to do this, what I've done, I've simulated a compact pole scene using the PS compact PPF, and then using that simulated compact pole image, I applied the PS Recons PPF to reconstruct a pseudo-full polarimetric scene. Then using the pseudo-quad image that I have from PS Recons, I went ahead and I used the CEBA PPF to generate decomposition parameters, notably alpha angle and entropy, for each CTLR and the pi/4 mode. So if in the demonstration, what I would have done, I'd go through each of these steps right here, and at the PS compact step, you have the option of choosing either CTLR, DCP, or the pi/4 mode. So what I've done, I've ran the PPF twice, once with CTLR and the second with pi/4. And then we're going to use those two images to compare the results between each other and to the full quad image.
So here I have the results of workflow 1 already laid out. I'm going to quickly go through each step that was outlined in workflow 1. So the first thing that's required, and this basically applies to all SAR projects, is I need to run the SAR ingest PPF, which will take my SAR imagery and then ingest it into a format for processing in PCI software. And upon ingest, it's going to apply a calibration type as well. So for this application, I've chosen a sigma naught calibration. Now the next thing I'm going to want to do is use the PS Boxcar PPF. And this PPF is going to be used to eliminate a lot of the speckle that you see in your imagery. So if I flicker between my two images right here, you'll notice that my PS Boxcar image is much smoother than my initially ingested image. So using my PS Boxcar image, I can now simulate a compact pole image. And to do this, I'm going to start off by opening up the algorithm librarian, and I'm going to bring up the PS compact PPF. And the PS compact PPF is used to simulate a compact pole image from a full polarimetric image. So what I'm going to do here, I need to specify 3 parameters. The first parameter is the input parameter. And basically, I need to specify all the matrices from my PS Boxcar image. Next, I need to specify an output. And the third parameter, I need to specify the compact pole mode. So with the PS compact PPF, you have the option of using CTLR, DCP, or pi/4. For this application, I've chosen CTLR and pi/4. So if I close this and we go have a look at the results, for my pi/4, my CTLR image, I have 3 matrices. For pi/4, the first 2 matrices are basically the horizontal and vertical 45-degree segments. And then for CTLR, we have the right circular horizontal and right circular vertical as the first 2. And the third matrix is basically the phase relationship of the first 2 matrices. So if we have a look at the results visually, and I flicker between both my pi/4 and my CTLR image, you'll notice there are some slight differences. Now the next step is I'm going to want to construct a pseudo full quad polarimetric scene. And that's the purpose of workflow 1. I'm going to want to take my compact pole image and reconstruct it. And this is done quite easily using the PS Recons PPF. So if I bring up that PPF, all you need to do is specify 2 things. The input, which is going to be all the available layers from your compact pole image, and then you simply need to specify the output. So it's quite easy. All you need to specify are 2 parameters. So if we have a look at the results of what that produces, for both my Polarimetry, my CTLR image, it's going to produce a new image with 6 matrices. Now in comparison to my PS boxcar image, there are 4 matrices that are missing. And this is basically due to the fact that with compact pole images, or with compact pole, the satellite transmits 1 signal and receives 2. And in comparison to full quad, the satellite transmits 2 signals and receives 2. So the fact that we're only transmitting 1 signal, there's a loss of information right there, and that's why we're missing those 4 matrices. So now using my reconstructed pseudo quad image, I can now extract my decomposition parameters. And I'm going to do this using the SIBA PPF. So basically the SIBA PPF is a Claude-Pottier decomposition method. So for the last part of workflow 1, what I'm going to want to do is use my pseudo full quad image, and I'm going to want to extract some decomposition parameters. And I'm going to do this using the SIBA PPF. So if I bring that up right here, the SIBA PPF is basically a Claude-Pottier decomposition method. So to run this, all I need to do is specify an input, which is going to be all the available layers from my reconstructed scene, and the output. And what that's going to produce, it's going to produce 4 layers: entropy, anisotropy, alpha angle, and beta angle. So now I'm going to take entropy and alpha angle, and I prepared some results in PowerPoint that compares those 2 decomposition parameters from my compact pole scenes to my full quad scene. So let's go back to the PowerPoint presentation.
So if we jump straight to the results, here we have 3 images of entropy for each of my modes. So from left to right, I have Polarimetry, I have full quad, and then I have CTLR. Now if we compare both Polarimetry and CTLR to full quad, there's a few differences. And we notice about the mixturing of the scattering mechanisms. So for Polarimetry, it seems there's a greater amount of mixing of scattering mechanisms in the water, as you can see in the highlighted areas right here. And in urban areas, there seems there's a greater amount of mixing, and in urban areas, the amount of mixing doesn't seem as high as the full quad scene. So it seems a little lighter in the Polarimetry than the full quad. Now for my CTLR scene, there doesn't appear to be any noticeable difference. But let's have a closer look at the distributions. So if we look at the alpha distributions, so right here I have actually the plotted entropy distributions of each scene. And the arithmetic mean of each of those distributions is plotted by the vertical dashed lines right here. So there are a few things you'll notice about these distributions. For one, all 3 distributions are bimodal. So that's good that the reconstructed scenes captures this property. Now in the previous slide, I pointed out that my Polarimetry scene had some notable differences in comparison to the full quad. So if you compare the Polarimetry, which is blue, to the full quad, which is green, you'll notice that at both peaks, the Polarimetry has a lower kurtosis, and the shape is not quite the same. Now if you compare the CTLR distribution, which is this lipstick red beige right here, to the full quad image, you'll notice that they're much more similar. However, the CTLR distribution overestimates one peak and underestimates the second peak. And if we finish off by comparing the means of the distributions, we'll see that our our CTLR is much closer to the full quad than it is from the Polarimetry. So the second decomposition parameter that I generated is the alpha angle that categorizes our scattering mechanisms. So if we look at smooth surfaces, trihedral, such as water, you'll notice again that pi over 4 is the most dissimilar, with slightly higher values. Now if we compare in urban areas where we have, if we compare where we have dipole scattering with around 45 degrees of angle from our two reconstructed scenes to our full quad, you'll notice that pi over 4 has much lower values in this mixed forested area right here in comparison to full quad. And the CTLR scene is much closer to the full quad. Now if we look at the distribution of the alpha angle, you'll notice that the two comments I made about pi over 4 can be seen right here. So looking at the first peak, you'll notice where we had trihedral scattering, so smooth surfaces like water, you'll notice that the peak for pi over 4 peaks a bit after our full quad and our CTLR image. Then you'll notice that in the dipole scattering region, the pi over 4 distribution peaks before both the CTLR and the full quad. And finally, comparing CTLR to full quad, once again you'll notice that they're very similar. Even if you look at the means, they're almost identical. Now the purpose of the second workflow is to compare decomposition parameters generated from compact pole imagery. And to do that, what I'm going to do, I'm going to take my full quad image again, and I'm going to simulate a compact pole image with PS Compact. But instead of reconstructing a pseudo full quad image, what I'm going to do is go directly to PS ComDis and PS ComDec. So PS ComDis basically is similar to, what is it called? The Claude-Portier method for decomposition. So it's going to produce alpha angle and entropy, but it's also going to produce 9 other discriminators that Gabriel presented previously. Then the PS ComDec PPF, it's going to produce 3 decomposition parameters: double bounce, volume power, and surface roughness. So once again, I simulated a compact scene using both the CTLR and the pi over 4 mode, and now we're going to have a look at those results.
So for workflow 2, we're going to start from our simulated compact pole scenes. And I'm not going to run a lot of the same processes that we saw in workflow 1. I'm simply going to run 2 PPFs to extract our decomposition parameters, PS ComDis and PS ComDec. So the first PPF I'm going to use is PS ComDis, and that's similar to the Claude-Portier decomposition method that we saw with the SIBA PPF in workflow 1. And what that's going to do is going to produce a lot of different polarimetric discriminators using the 4-element Stokes vector. So if I bring up the PS ComDis PPF, there are only 2 parameters that we need to specify. For the input, I simply need to specify all the available layers from my compact pole image, and then simply specify the output. If I close that and we go to see what it produces, it's going to provide us with 11 discriminators. And if you look at the last 2 right here, we have entropy and alpha angle, which we saw in workflow 1. So using these 2 decomposition parameters, discriminators, I'm going to compare them once again to my full quad scene. Now the second PPF I want to look at is PS ComDec. And PS ComDec is similar to the full polarimetric Freeman-Durden decomposition model. So if I bring that up from the algorithm librarian, simply search PS ComDec. Here's a PPF. And there are 3 parameters that I need to specify. The input parameter, which is basically going to take all the available layers from my compact pole image, specify the output, and then I need to specify the decomposition type. Now for this application, I've chosen the M-alpha decomposition, which relates the Stokes parameters to the degree of polarization of the scattering mechanisms. So if we close this and have a look at the results, we've actually produced 3 layers, which are double bounce, volume scattering, and rough surface. And the 2 extra layers right here, I produced them. I simply normalized my values for better interpretation. So with all these decomposition parameters from PSComDec and PSComDis, I'm going to now compare them to their full quad equivalent. So let's go back to the PowerPoint slides and have a look at the results.
So we've started off by looking at entropy and alpha angle produced by PSComDis. So you'll notice that, if we start off with entropy, and we look at smooth surfaces right here, you'll notice that this time both CTLR and pi over 4 seem to be a little higher than our full quad image. But if you look at the CTLR image right here, you'll notice that overall, all the values, the pixel values, seem to be much higher than both the full quad and the pi over 4. Now if we look at those distributions, you'll notice that the first thing that pops out is the peak of the CTLR image. You'll notice this time that it's much higher. You have a much higher kurtosis than the full quad image. And then if we look at the middle portion in between both peaks, you'll notice that pi over 4 overestimates the full quad and CTLR underestimates the full quad. And both the both the CTLR and the pi over 4 at their first peaks have higher values than the first full quad peak. Now here you have a comparison of the reconstructed and the compact pole distributions. So you'll notice there's quite a bit of differences between both images, notably with CTLR. If you look at the second peak, like I mentioned earlier, the CTLR peak is much higher. So looking at the second decomposition parameter, alpha angle, the first thing everyone notices is the very bright pi over 4 scene. Basically, the bulk of the values for that scene range between 50 and 70 degrees. So clearly the pi over 4 configuration is not ideal in this circumstance. So if we compare the CTLR alpha angle to the full quad, I'm going to completely disregard the pi over 4 for this one. You'll notice that the CTLR results are much lower. So looking at a smooth surface right here, you can see that the values are lower. And if we look at the dipole scattering in this mixed forested area right here, you'll notice that once again the CTLR's values are much lower. So if we go have a look at the distribution for those 3 images, the first thing you'll notice is that that bright pi over 4 scene has a density distribution that's very dissimilar to both CTLR and full quad. And the second thing you'll notice about these distributions is that neither pi over 4 nor CTLR are bimodal, unlike the full quad image that is bimodal. They're both unimodal. So in this circumstance, we see right here that the CTLR image, the alpha angle image for CTLR is the one that's the closest to the full quad. So if we compare with what we had previously with our reconstructed distributions, we'll see that there's quite a bit of differences right here between both. So at the top we have our reconstructed, and at the bottom we have our decomposition parameters, the alpha angle, extracted directly from a compact pole image. So now I'm going to move on to the results of PSComDec. And the first decomposition parameter I'm going to look at is volume scattering. So if you look at the results, you'll immediately notice that the full quad scene has much higher volume scattering in urban, forested, and agricultural areas. And between the CTLR and the pi/4 scene, it appears that the CTLR scene resembles the full quad the most. However, they're both quite low. If we look at those distributions, you'll notice that neither CTLR nor pi/4 truly represents volume scattering in voluminous areas for this application. And you'll notice that right here, when you look at the full quad distribution, and neither pi/4 or CTLR fully extends the same spread as full quad. Now the last decomposition parameter I'm going to present is double bounce. So looking at the pi/4 scene, we can immediately determine that the double bounce is overestimated right here, and that the CTLR scene is much closer to the full quad. However, in the CTLR scene, we can still spot some areas where double bounce is either overestimated, such as this forested area right here, or it's underestimated in built-up urban areas. So if we have a look at the distribution for the double bounce, we can see that the shape of the pi/4 is quite different. There's no peak right here like you would find with CTLR and full quad, and it kind of spreads out much further than both CTLR and full quad. And also, if we look at the mean of pi/4 right here, you'll notice that it's very dissimilar to the mean that you have for CTLR and the full quad image. So to summarize what I've just demonstrated, using a full polarimetric image, I simulated two compact pole images with different modes, CTLR and pi/4. Then I extracted decomposition parameters from reconstructed and compact pole images for comparison. Now the most important thing to take away from this demonstration is not the comparisons I've made, but it's actually how easy it is to process compact polarimetry imagery. Now, I wasn't able to show that to you, but essentially every PPF that was used to produce these results, all you need to do is basically provide an input and an output, and specify an output, and then some of them have a third parameter, basically which is just the mode that you choose to either perform the decomposition or the polarimetric mode that you want to simulate your compact polarimetry imagery. So it's actually very easy to do. If you would like to acquire any more information about radar tools within Geomatica, you can have a look at pcigeomatics.com, where we offer plenty of resources such as training material, our white papers, and also PCI, where we have a partnership with MDA to provide access to radar Sat2 imagery. And all this is provided on our website. So please have a look if you have any more, if you'd like to get more for radar suite processing.